Alright, so we'll continue with our discussion of the modeling of an antenna, and we finally come to the part where we get to use computational electromagnetics, right. So, what we said earlier was that in a realistic scenario, imagine an antenna, I connect some voltage source to it, okay, some RF source. I wanted to broadcast some information. The trouble we said is that we do not typically know how is the current distributed along the length of the wire. I mean, I know what is the voltage at the current at the point I have connected, but across the length I do not know what is J as a function of space. So, how can I calculate A, how can I calculate H, how can I calculate E? So, what we will do is we will use the CEM theory to find out what the current is, and what will of course help us is boundary conditions. Okay, that is the one thing that always fixes things in nature, right. Boundary conditions will force, for example, tangential fields to be conserved, fields to be 0 on a conductor and so on. Okay. Now, let me warn you that modeling a realistic antenna is quite complicated. So, in order to give you a first demonstration of how to do this computationally, again we will make simplifying assumptions. Okay. So, one of the simplifying assumptions will be we will take our current source to be, let us say, along the z axis, but very thin. We will make the wire to be very thin. Okay, so thin wire over here with the radius to be A. Alright. Later on we can sort of appreciate how to make it bigger, but you will find that even making keeping this radius to be thin is itself a challenging problem. Okay. So, the only thing is we are not making it infinitely thin, it is small compared to lambda, right. So, this radius of wire is equal to A, which is much less than lambda. That is the assumption. Okay. Under this assumption, we can again sort of make a claim that the current is going to be z directed, right. The current is going to be going vertically up because the radius is very small. So, we are not going to have things like a current that is spiraling and going up, right. That may happen as the radius becomes bigger, then that is happening, but if this dimension is very small, mostly the current is just going up. Okay. So, z directed currents. Okay, this is also an assumption. So, these are the two assumptions that we will make, okay, and based on this we will see how can we solve this. Now, when we had derived the integral equations in terms of this magnetic vector potential A and scalar potential phi, this was a choice which we had made for the divergence of A, and what did we call this? Lorentz gauge condition, right. So, this was our how will this get simplified under our assumptions? What components, remember A is of what form? A is of the form mu times J convolved with G, right. So, what form will, how can I simplify this a little bit more? Louder? Divergence will be, A is only in the z direction, right. So, the vector A has which components? Only the z components, right, because A is coming from J over here, and if J has only a z component, A will also have just a z component, right. So, my A is going to be equal to Az z hat, right. So, this will simplify to J by omega mu naught epsilon naught partial with respect to z, right. So, that is useful. The next thing we had was a relation for the electric field in terms of the potential, right, that was this relation over here. So, we are not going to go to the magnetic field, we are going to go the second route to the electric field. Okay. I could have also gone from H and then from H to E. Any guesses why we are going directly to E? from A and phi, why am I going to E? Say again, the magnetic vector potential is? No, this A is the magnetic vector potential. Yeah. Yes. No, we can use? No, that Ohm's law is not, Ohm's law is sort of valid in a resistor. Here there is a little bit more complicated, right? J is not going to be proportional to E. My question is that normally what did we do to get the fields once I got A? How would I write? H was 1 by mu curl of A, right? And I can find, no, my question is this, I have from A, I want to get to fields, right? So, I can go from, once I get A, I can go to H, and from H I can go to E by taking curl of H. But instead I am writing E directly in terms of A and phi. Here I have to do more work, right? I have to also find phi. Earlier if I used only A, I could get H straight away. Okay, so this is the part of sort of looking ahead. When I write down my Maxwell's equations, how will I enforce anything? What will help me to solve a problem? Boundary conditions. Boundary conditions are what are going to help me solve. If what is a reasonable assumption for a metallic wire? That's a perfect conductor. On a perfect conductor, what kind of boundary condition can I impose? Can I impose it on H or on E? E, right? Because inside a conductor, electric field is 0. So, that is the goal, that is the sort of property I want to utilize. Fields inside a conductor are 0. So, for that I need electric field. That is why I am going from A to phi, that is why I have written phi over here, and phi and A together is going to give me E. Okay. So, that is just sort of planning ahead why I am writing the electric field. Magnetic, there are, no, how do you apply tangential conditions on H in a conductor, in an electric conductor? Yeah, so it's simpler to deal with a field which is itself going to 0, that is the simplest boundary condition, right. So, how does this E get modified now or simplified rather? This will become minus j omega A, and this grad phi will become grad phi is not a constant. So, I will replace, so E z, this will become A z minus j omega mu naught epsilon naught, right, second derivative of Z2. Okay, so let's take all of these terms outside over here. So, I am going to get a 1 by j omega mu naught epsilon naught, and I am going to be left with a k squared A z plus okay, I have just taken omega naught mu naught constant outside. Now what? Now I have to use this property over here, right? I will remember what my objective is to somehow solve for the current, right? Yeah, once I get J, then right. So, I have to put in this expression for the magnetic vector potential over here. So, what is my A? A's. Right. So, I can write Az in terms of this convolution, right? In terms of mu Jz convolved with G, right? And G is of what form? E to the minus jk r by 4 pi r. Yeah. Yes, that's where we use this assumption. It's not a function. Yeah, because they're all going this way. There is no swirling around over here. If the radius is not small, then they could swirl around. Then it will become a function of x and y and z, right? Imagine a helix, right? Where I am on the helix also depends on x and y, no, not just purely z. So then that this assumption will become, I mean, it will not be correct over here. Alright. So now what I can do is I can write down this whole field in terms of a convolution. I am going to replace A by the convolution, right? So I can write over here this E z is equal to 1 by j omega mu naught epsilon naught, okay, and write this convolution like this. So in general 3D convolution, right, I have this is the most general expression, right? G convolved with J. Okay. I did not write the prime coordinates, but you can imagine this G is going to be G of R prime, this is going to be J of R prime, okay, and this is going to be E Z of R. Right. So, I am integrating over the prime coordinates. Okay, so we have got an expression where I have the electric field on the left hand side. Is it known so far? Is the electric field known? So far it seems like it is not known. I mean, what is the electric field? So, I mean, we have to come to that. So, I am going to put a question mark over here. G is known, J is not known. Okay. So, what can we, I mean, there are too many unknowns in this problem. If I don't know E also and J, there is no way I can solve it. But do I know E? Yes, that because anywhere inside and on the surface, what is the electric field, right? E total is equal to 0, right. Now, this electric field that I have written over here, is it the total electric field in this equation 1? Is it? This is the field that is happening. So, imagine that there is a plane wave that is falling on the antenna, alright. That plane wave is inducing a current on the antenna, okay. That current is this J. So, how many total fields are there? There is a field that is produced by this current, by the induced current, and then there is a field that was already present due to a source. In the case of a receiving antenna, it's a wave that is falling on the source. In case of a transmitting antenna, there is going to be a field that is produced by the generator, right. It may be localized. For example, I connect a voltage source across some point. So, there is an electric field here, but not somewhere else. So, in general, this is going to be E incident plus E scattered, right. So, this is actually the scattered field over here. Scattered means scattered by the, I mean, due to the induced current. Yeah, but that it does not cancel off the E incident in some sense. I mean, you cannot forget about the E incident. Okay, so that is why the total field is composed of both of these, and both of these together are 0. So, this equation 1 then gets simplified into, this is equal to minus E incident. Right? I am going to write E incident on top and put a Z over here, because I am only talking about the Z component. Yeah. Yes. No.
We can call it because we are only setting the source. So that's the sort of
Yeah, okay. So, we will come to source modeling later, but let me just give you an example. Supposing this is my antenna, okay. I have connected some voltage source across it. So, this voltage source is going to produce some electric field inside over here, right. So, that incident field is valid only over there, right. Outside the voltage source, you are not going to find any electric field, but this has now produced a current over here, right. So, you have both of them over here. This current in turn is going to produce a scattered field. The incident field is going to be there. So, if I consider some point over here, there will be the incident field due to the voltage source and due to the field that this J is beginning to produce. Both are going to be there. It is not that because I connected this, now I can ignore the field produced due to induced current. So, remember, right, induced current produces a field and they call it a scattered field, not induced field. Okay, induced current, scattered field. These are the two terms you should keep in mind. Okay. So, now I know this question mark becomes a tick mark. I know this the left hand side, I know the induced current and the scattered field therefore, and I know everything in this except J. Now, J is appearing inside the integral sign unknown. So, what kind of an integral equation is this? Fredholm integral equation of first kind, right. Alright. Now, if we were to go and solve this as it is, it is going to be a little problematic because there is a 3D convolution over here, right. So, let us see how we can modify this.